Hi everyone once again, and we're back with Daniel Paulus here. Hi Daniel.
Hello.
Daniel is an engineering manager at Contentful in Germany, and previously Daniel was responsible for low-level USB programming and reverse engineering iOS and Android internal APIs to build stable new features on inherently unstable consumer devices. Before that, Daniel held roles as developer, team leader, IT manager, and project manager during his 13 years career as an officer in German military. And now we're gonna hear and see the talk named Reverse Engineering iOS, Screen Mirroring with Golang. So the stage is yours, Daniel. Enjoy.
Thanks a lot, Daria. All right. So yeah, let's get to it right away. So just as Daria told you all, in my last job, I reverse engineered quite a few things, iOS and Android, because we were running a real device testing cloud, right? So we had actual Android and iOS devices in server racks and made them available for our customers to run their tests on. And so how all of this started, one of my first tasks when I got into that job was make the live testing experience faster, right? So usually these providers, they give you kind of a remote control for, arbitrary devices in the browser. So you can just, choose a, iPhone 6 or something, and then you get a live stream from the device into the browser. You can click on it, test your app, and do whatever you want. And live testing was had a pretty low frame rate, and so my first task was make that faster. So we were looking at different options, and of course we were Googling around. And one of the things that you would find back then was a video of someone reverse engineering the QuickTime feature that lets you record iOS device contents or screen contents, like you can see in the background. Right, so this is basically a macOS QuickTime feature that lets you do a screen recording of any iOS device. And we looked at this one, but at the time we thought it would probably be too complicated. And I then happened to stumble upon a cool internal private API of the XC-test framework, so we could just do it without QuickTime. But if you're anything like me, you just cannot let a challenge like this rest, especially because at the time there was a video online where someone already reverse engineered it, and they, did like screen recording on Ubuntu, and it just drove me crazy, right? I thought like, I want to solve this also, and the question was, so how would you do that, right? How would you solve such a problem and build your own QuickTime screen mirroring? So first, of course, let's Google it, right? Like I said, then you find this video on YouTube where someone already did it, and you're like, yes, so it's possible. You look at all the comments, and you see people requesting the source code, but there wasn't any, so meh. So then you keep looking on Google, and you find some discussions online, but nobody has a solution, so and there's no source code anywhere. And of course, the final conclusion is, how hard can it be, right? So how do you approach a problem like this, right? So you have this private feature. There's no documentation. Where do you start reverse engineering this? And then usually you have two ways to find out how something like this works. So the first and probably more obvious one is you can try and understand from the code. So you figure out the binary that actually does the magic. You disassemble it and try to understand it using static analysis and a debugger. So what's a disassembler for those who don't know? Basically, it's a tool that lets you take a binary and then reconstruct some kind of C code-like code from it. But as you, of course, see, the compilation of code is a one-way process, so what you will get out of it is basically something that doesn't contain any abstraction. So you lose all the method names. And and much more. And it's basically very complicated to understand this. It's possible, but it's very, very hard. So let's think about what else we could do, right? So instead of looking at the binary, we can also just think about, maybe we can just eavesdrop on the communication, right? So whatever video screen mirroring stuff is happening, it's going over the wire, right? So if we had a way to look into the raw binary, maybe we could just figure it out from there. And in this particular case, it was going over the USB connection. So luckily, nowadays, this is extremely easy and cheap on macOS. You only have to run this command, and then it opens up a virtual USB interface that you can just eavesdrop on using Wireshark. So that was pretty good. And just to explain the problem from a different angle, right? So similar situation, let's assume you want to reverse engineer a REST API. And, just as a comparison, what would you rather do? Read obfuscated, complicated JavaScript code to understand what it does? Or maybe it's also cool to just look at the HTTP requests that are being made and try, look at the endpoints and try to reverse engineer the API from there. And this is pretty much what I did. So I open Wireshark, I start playing the video, I stop playing the video and save the capture. And then USB may work with packets internally, but I assume that the data is sent as some kind of stream of media samples. So I write a little Python script to extract and save all the bytes received and sent in a separate file. And then, and I promise you, this is the only text-heavy slide in the whole presentation. And then I get this, right? So we instantly see one very important thing. Luckily, the data is not encrypted, which you can see because you can actually identify things in here, right? There's some strings that you can see, and so the data seems to be not encrypted, which is great. But still, how the hell do you make anything out of this, right? You see some strings, they seem weird. You can Google them, but it won't help you much. So let's think about, how can I solve this? And how can I figure out what this all means? So one of the things I like about reverse engineering is you have to make theories about how the people who built this have actually implemented it, and then you can try and see different approaches of how they could have implemented it and just see if one of the pattern matches. So if you think about network connections and network streams, which gives you an endless stream of bytes, how do you know when a message is complete, right? And there's basically 3 ways you could do this. So either there's the fixed length standard, right? So 20 bytes are sent and they form a whole message, another 20 bytes, another 20 bytes, and so on. You have delimiter-based messages that always are finalized by some kind of delimiter that's always the same. And then you have the one that sends you a 4-byte integer containing the length of a payload, and then you get a bunch of bytes that represent that payload. So let's look at this, right? So can we do fixed length here? Fixed length will be something like this, right? So you take the first line, then let's assume the same amount, and it still looks good. Just look at the structure of the binary. If you go here, it seems to be still working, but if you look at the 4th line, it doesn't make any sense anymore, because usually you see like 4 bytes here and then some kind of string, and then here we hit a string. So that's probably not fixed length. It doesn't really make sense. Also, if you think about it, I mean, we are expecting media samples, right? So we kind of expect them to be variable length. So let's look at how would we figure out if it's delimiter-based. So if it were delimiter-based, then you would see the same byte sequence popping up a lot of times, right? Because it would be delimiting the individual data. You don't see it here, and even if you look at the long hexagon, there is no such a thing, right? So it's also not delimiter-based. So let's look at let's try 4-byte length-based, right? And I marked, as a convenience, I marked it here. So this would be the 4-byte length. And I wrote a little code snippet so we can run this. It's a bit dark. Let me just mark it. So if you put in the 10,000 4 bytes in here, and you compute ASCII, you compute an integer from this, so a decimal representation, you will see in little endian it's 16, and in big endian it's like a ridiculously huge number. So you're thinking, okay, that's 16, let's try it. So you go 16 bytes from here, and you see, oh, this is where we land. So that looks pretty good. Here's another 16. So you get here, and here's a 24, and we can just see what happens. Let's run 24. And wait, that was the wrong one. Sorry. I want to do little endian. 24, run this. And you see it's 36. And if you go 36 bytes from here, you will see that you just, come to the next message, which starts here. And you're like, yeah, so that's what it is. It's 4-byte length. Nice. So we have the frames, right? So we know how the messages are separated. We know that you get 4 bytes length and then you receive the payload. But then you have all these kind of strings that don't make any sense, right? And you're like, what's a GNIP? Like, what does it mean? So again, we run a piece of code, and I used some Go code, and what it does is it takes the hex of this string, like GNIP, and it calculates ASCII representations, and then we think about, wait a second, if the length field was little endian encoded, maybe those are 2 little endian encoded integers. And so for those of you who don't know what little or big endian is, it's basically just the way that you read the byte. So from read the integer, so from left to right or from right to left. And if you read GNIP from right to left, then you will realize this is actually ping. And suddenly it all makes sense, right? If you then reverse all these things, then you were like, oh, of course, that's what it means, right? So you see, a string key, you see integer keys, you see Boolean values, dictionaries, data values, and you're like, okay, that's how it works. And then slowly everything starts to unravel. And as you go through the hex dump, you will find ping packages and asynchronous ones and synchronous ones and reply packages. And then let's look at the individual ones and see what they do. So first one, ping. That's boring. It's just for saying hello. It's kind of a handshake. How do I know that? You will find this packet only twice in the whole byte stream, right? Just when you connect, you send a ping, you get a ping back, and then the communication starts. So boring, simple, got it. Next. You got these asynchronous packets, and if you look through those, you will find this sbuff field, right? And so sbuff was actually the first time when I Googled something and I could find something interesting. I was Googling sbuff, and then I found a presentation about Apple's core media framework. And I figured out that sbuff was actually the favorite variable name for CM sample buffer instances. So I was like, it's probably that, right? It's like there's the chances very high. And if you look at the publicly available header files for CM sample buffer class, then you will see that it pretty much matches these strings that you will find here, right? So you have like an output presentation timestamp here, for example, OPTS. But we want to extract video, so let's look at the interesting stuff. And this is the sample data, the other one that I marked, right, as that. So let's check out the sample data field and let's see what's in there. We extract it and we see this byte, like this hex dump, this byte array. And now let's try the same trick as before, right? We think maybe it's maybe it's 4-byte length and then payload. And you run the 1E and you see that the little endian decimal decoded value is way too big to be a reasonable size. And then you see the big endian one, it's 30. So yeah, that makes sense. If you look at the integer, it's a 1E, so 30, and if you go 30 bytes ahead, you will land here. And we can try putting this value in. So 0, 1, 62, and then finally 58. So let's run this. And what you will see is a big endian result of 90,712. And if we had the full hexdump and we went there, we would actually see that this is where the sample ends. So congratulations, we nailed this one. It's big endian encoded, but now that we know the framing, or we know where the messages are, so let's see what the payload format actually is. And so this is an extracted example from what we saw before. And to make the long story short, I read a lot of documentation because there was, the obvious thing is that it's probably going to be some kind of H.264 video sample, right? I mean, most cameras produce that format or that encoding, and so it's safe to assume that this is probably it. So what I did was basically read a lot of documentation about how H.264 is encoded and how it works. And if you do that and you look at the header, you will realize this is actually a H.264 network abstraction layer unit, a NALU. So, and this is at the time when I was able to extract all these things from a hex dump using code, and I just wanted to have a playable file as a proof of concept. So, reading the H.264 documentation, right, and it will spare you the details. This is basically enough to create a playable video file. So you use 1 as a delimiter, which is, by the way, a great example for a delimiter-based byte stream format, right? So you write a 1, you write the network abstraction layer unit, you write another 1, next unit, and so on. And this will result in you getting a playable video file. And at that point, I was basically able to use a 10 megabyte hex dump and create a video out of it, which was pretty cool. And so usually I check the audience if someone is sleeping. I cannot do that right now, so I hope that you're all still awake. I made some effort to also to create a documentation. It's on the GitHub repository with the link. You will get that one later, and it contains basically every packet that is being sent with a description and example payload. So if you want to check out how this works or write your own implementation, you can basically do that. All right. So the first prototype I did was written in Java. So why would you use Golang for this? First reason, USB programming is extremely simple. The Go USB package is really cool, right? You would assume that programming USB devices is actually hard, but then if you look at this code, it's not. This is basically all you need to start sending and reading data from USB devices. So very simple. Next. You have, and every Java programmer will know what I mean, you have signed and unsigned primitives, which is amazing, right? Because usually in network protocols, you have different integer values depending on what protocol you have. And so like I said, Java only has signed variables, so it's always kind of hacky to get it right. And yeah, with Go, you can just do that. And then even you can do awesome stuff like, let me see, do I have that? Oh wait, that's next. So you working with byte slices is so cool for this. If you want to write your messages, you can just take the formatting, little or big endian, put unsigned integers, and you can just put them in byte slices. So it's really easy to write these network codecs. And that's what I want to say. You can even, and this is especially cool, you can even write and read structs directly from byte streams, like in C, which was really helpful. If you look at this code snippet, I basically just copy pasted the cmTime struct directly from the Apple header files, and yeah, that's how my network codec works. So that's really great. And one interesting question is, so how would you unit test something like this, right? So you have no idea where you're going with this. You're writing code, and while you're reverse engineering and figuring out stuff, so you have no clear vision of what the end result is going to be. And what I did was basically use like the golden file approach, right? So I mean, I knew what the messages were supposed to look like, so I could, using golden files, build really great unit tests for my codec. And of course, if you're sure that the codec works, then and something else doesn't work, you basically know where not to look. And this was really helpful while reverse engineering this, because of course, it never works on the first go. But if you're sure that your codec works correctly, then this is a great help. Oh yeah, you can see some sample code here. So I created individual test fixtures and binary files for every message type there is. And then basically make an assertion that my decoder does the right thing, and also that the bytes that come out are the same as in the file. So why does reverse engineering make you a better engineer? I like that, you have to be very tech savvy to make theories on how they built it and then test your theories one by one. Right, so you think about stuff and you think about, so if I were to implement video streaming, how would I do it? And you think about how could the network protocol look like, and you test basically using your knowledge as an engineer. You test all these theories until you figure out the right one. Writing clean unit tested application code without knowing the end result was also a challenge for my testing skills, which I enjoyed. Right, so this just helps with TDD and getting better at it. Then, of course, you learn so many cool new things. Like you can really dig into networking basics, right? So how are codecs written? How does it all work on a low level? I learned how H.264 works and how it's actually encoded on a binary level. I learned USB programming, which was a lot of fun. And then I think one thing I always like to say is, like, one of the most useless skills I probably ever learned is if I look at a hex dump now, I can actually tell you if it's a WAV file or not, because I'm able to read raw WAV audio. Yeah, and so it's the low level, and this is something that I really like. There is no magic, right? So oftentimes, I remember back when I was a kid, we had this like hard drive recovery tools, and I would always ask myself, like, how does it actually work? If I delete a file in Windows, why is the tool able to recover something? And then doing these low-level tasks, you at some point realize, files were basically just tables and byte sequences, and there's documentation that tells you this is what a JPEG file looks like, right? So it always starts with the same 4 bytes, and then then there's the metadata, and then there's this header, and then there's the payload, and this is where the image data is. So you actually understand how these things work on a very low level, and you see that all of it is actually pretty simple. Plus, and that's a late add-on, a lot of people shared their story when they saw the repository. So that was really fun talking to a few folks who are also in the same testing environment, and yeah, just showing them that it's not that hard to be done. And so I do have a little demo, so you'll actually believe me that I did it. No, it doesn't work. So you can see me running this on my personal iPhone 10, and in the background, you can see this running on Linux. Boom. So yeah, I don't think we can go over GStreamer. We're pretty short on time, so that's basically how it works. And so you can check out the Golang reference implementation on my GitHub. It works in Linux. It works on macOS. It is never going to work on Windows because you cannot. There's just no cool. There's just no cool library for doing USB programming on Windows. On macOS and Linux, you can use libUSB, and that's actually fairly simple. And that's also what GoUSB uses. But on Windows, there's nothing like that. So it's you cannot do certain things. You would have to write your own driver, and I was not interested in that. So it's there's no Windows support. If someone wants to build it, then please go ahead. It supports custom GStreamer pipelines, so you can very easily take that video and RTP stream it, or add WebRTC on top, or convert it to whatever file you want. You can save audio only, whatever you like. It's super easy to do with GStreamer. And you can ask me all questions about iOS. So I spent quite some time of my life understanding how iOS devices talk to macOS machines. So I basically, if you ever wanted to know what actually really happens when you see an Xcode app is installing, I know exactly what happens. You can ask me questions about Contentful if you're interested, about the company, and about everything else. So thanks a lot for listening, and I hand it over to Daria.
Thanks a lot. Awesome talk and cool demo at the end. Okay, let's see what questions you have. Okay, the first one is from Matt Ryer. If I read out the bytes for a WAV file, can you tell which song it is?
No, that I cannot do. I can only tell you if it's a WAV file, if it's a legitimate one, but I cannot sing it. That's beyond my skills.
Okay, the next one. Why is there a mix of big endian and little endian in single protocol?
Yeah. So I assume that whatever is encoding the H.264 is probably a different component than the one software component that's wrapping and taking the H.264 stream and then wrapping it in this Apple Core Media framework kind of protocol. So I guess that's the reason, right? So no one cared to transform it, or it's just to make it harder for reverse engineers. I don't know. But no, I don't think, seriously, there is not a good explanation for this. But this, so probably whatever component creates the H.264 just has big endian encoding there. Yeah.
Okay, good, thank you. Oh, and another one from Matt. How would those of us who don't read the H.264 protocol reference documentation before bed realize that was the format?
Mm-hmm. Yeah, this is tough, right? That's what I said. It's a mix of getting lucky and kind of guessing the right things. So I would just assume that if it's a video stream, it's probably not using anything custom. Like nobody in their right mind would build a custom video encoding format. So the idea is take the most popular formats and just try them one by one and see if it makes sense. And H.264 is like the default encoding that pretty much everything uses. So that was the first thing I tried. That's a strategy how you would solve it. So you really have to take the PDF documentation and then just try to match the table that tells you how H.264 is structured, and then look at the binary you have and see if it makes sense. If it had been a different container format, right, then I really would just have to go through all these one by one and see which one it is. But yeah, it was H.264, so I got lucky in the first try.
Okay, cool. Thank you. There's some more questions. Okay, why is there a mix? Oh, that was answered. Sorry. Okay, the last one. Do you have a good way to test for Indianness on your stream? Doing some hacky stuff for that. That's a question from Dylan.
I think I don't get the question. What do you mean? Like figuring out which Indianness it is?
Dylan, if you're listening to us, just type some clarification.
Checking the public chat.
Okay, I don't see anyone typing anything right now.
But I will be in the speaker's corner, right? So you can also just...
Yeah, Dylan, so join Daniel in the speaker's room, and you can ask the question once again there. Okay, let's wait for a moment if we get any more questions. And there is a clarification to know if the architecture you're running on.
No, I cannot tell you that. I wouldn't know.
Okay, so we don't have any more questions so far. So yeah, once again, Daniel, thank you very much. It was a very cool talk, and we get you can see in the public chat that people loved it.
Yeah,
thank you so much
for listening.
Thanks, and yeah, see you in the speakers room.
All right, cool.
Okay.
Bye.
Thanks. Bye-bye.